Okay, so we'll get started. I have to take an attendance, so please stay back after the class for people who have not marked their attendance for today. And I think today would be the last lecture when I have to take an attendance. So next lecture onwards, there's not going to be any attendance. Okay, so we were talking about linear systems theory. We talked about the motivations to study linear systems. We talked about vector spaces. We talked about field, and then we talked about field, then we talked about vector spaces, then we talked about linear independence. So we are going to continue our discussion on vector spaces, fields, linear independence, span, and so on in today's class. And then we'll talk about linear operators. I think linear operator is a very important topic. All of you have done linear algebra, so linear matrices is kind of a linear operator. So we'll just study it in the full generality today. And then we'll talk about norms and inner products and so on and so forth. Okay, so we have V is the vector space, linear vector space. I'm going to write it in the short form as LVS, linear vector space. F is the field. And I wanted to remind you of the typical examples for field and linear vector spaces. So field is RC, linear vector spaces is Rn, Cn, Pn, C, AB, Rn. So space of continuous functions from closed interval AB to Rn. Generally speaking, over the course of the lectures, this AB will become a time interval and Rn will become the state of the system. I know many of you are familiar with some form of state space methodology for control systems. So this space will be very important space for us in the subsequent lectures. Although in the past you have mostly learned about Rn, and to some extent you have learned about Cn if you have taken courses in signals and systems and optimization and linear algebra and so on. Okay. And then we were talking about so I have what was the other thing? Subspace. We talked about subspace. So W subspace of V, and essentially the example that we talked about, the polynomials over with real coefficients, is a subset of C, is a subspace of CAB R, and you can do it for Rn also, but then you have to take polynomials of nth degree with various exponents for each of the components of Rn. So anyways, this is the subspace definition. So remember, subspace definition was if you add two elements, it has to be in the subspace. So you pick two elements from the subspace, you add them up, it has to be in the subspace. You take an element, you extend it, you contract it, it has to be within that subspace. Typically speaking, 0 of V, this is contained in the subspace. So going back to our example in Rn, so I know a lot of you are familiar with Rn, Euclidean space. So any plane or a line passing through origin is a subspace. Okay. So you pick two vectors within the plane, you add them up, the resulting vector lies within that plane as long as it's passing through the origin, and then you take a line or a vector within that plane and you extend it, and it remains part of that particular subspace. So okay, so now we talked about linear independence as well. So we'll continue to build. So linear subspace. generated by W. So you pick a subset W as a subset of V. So I want to keep this example in mind. So my W is 1 S square S cube S raised to 4. My V is C A B R. So the space of continuous functions from interval a b to r. So I pick a bunch of polynomials. So constant polynomial s square s cube s raised to 4. So I have 5 elements in this space W. Maybe it's not the right notation. So let me put this in a right notation, because if I screw up the notation today, you might not be able to understand it for the rest of the semester. So let me write it as V0, V1, V4, and V0 of S equals to 1, V1 of S equals to S raised to 1, V2 of S equals to S raised to 2. Okay, so the continuous, and so I picked the subset of continuous functions from the interval AB to R. What are those continuous functions? Well, those are these 5 polynomials that I've picked. And I constitute a set W out of these 5 elements of this vector space, linear vector space V. Any questions so far on this? Okay, so how do we define the span? So the book is using the notation S of W. So book's notation is S of W. My notation, because I don't want to confuse this S with this S, it's quite likely that you might get confused. So I'm instead going to use span of W. Many math books also use span, so I think there won't be any confusion if I use the word span here. Span of W is summation of alpha I W I goes from 1 to n, such that alpha is in F, Wi is in W. And note that this is only finite sum. Okay, so I pick a bunch of elements from W. So W could be a finite set, it could be an infinite set, it could be countably infinite, or it could be uncountably infinite. You can pick arbitrary set, but then you pick finite number of elements from that set. You pick the corresponding field, like some finite corresponding, so n number of elements from the field F. Take the linear combination. Remember that this operation alpha I times Wi is a valid operation. That was something we defined in the previous class, because this is the vector. This is the vector in a LVS, linear vector space, and this is the field. And so the dot product is well defined, and then the summation is also well defined. So what I'm going to do is I'll take this dot product, I'll do this summation. It's a well defined element of this vector space V, because remember W is a subset of V. So I pick the subset of V. It could be a small subset, it could be a large subset. I take the linear combination of the vectors within this particular subset. What I get is like this set is known as the span of W. So what is the span of this W? It's all polynomials of degree 4, of up to degree 4. So let's see, is 2 plus square root of 3s, is this part of the span of W? It is part of W. That's because I am taking a real number, so I'm taking V0 times 2 times V0 plus square root of 3 times V1. That's part of W. What about 2 plus square root 3s plus 5s raised to 4? So this is also part of, sorry, I didn't mean to say W. This is a span of W. This is also in the span of W. Because I picked elements from W, I multiplied them by a field, which is in this case the real numbers, and I get something which is within the span. What about summation s raised to k over k factorial? K goes from 0 to infinity. Is this in the span of W? It's not in the span of W because now I'm picking elements s raised to 5, s raised to 6, s raised to 7, not part of the span of W, but is it part of the vector space V? What is this sum? Anyone remembers? Yeah, it's an exponential. This is exponential of s. Is this function a continuous function from the interval a to a and b to r? Is this a continuous function, exponential? It's a continuous function, right? So this is in V, but this is not in span of W. Okay. So you have elements in V which are not part of the span. So span, this particular term, actually generalizes hyperplane. So we talk about hyperplanes all the time. We've talked about it in optimization class. We've talked about it in linear algebra class and so on. So what is a hyperplane? It's a plane passing through origin. In our case, we are interested in planes passing through origin. So a hyperplane is a plane passing through origin or a line passing through origin in an n-dimensional space. This idea of linear subspace generated by W in V, it actually generalizes hyperplane. Let's see how. Any questions on this before I erase this side? So this is a hyperplane. Let me call it span of W. I have two vectors, W1, W2. I don't even want to take them as orthogonal to each other. It could be just in two different directions. W2. And these two vectors are actually spanning this particular hyperplane, span of W. So my W just contains two vectors, W1 and W2. So this is spanning the entire hyperplane, and what I'm doing is now generalizing that idea to potentially infinite dimensional spaces. So what the example that I just wrote is an extension of this particular idea in finite dimensions to something that is infinite dimensional. I know I have not defined infinite dimensional yet, but we'll define it very soon in like 10 minutes from now. Okay. So you can think of this as a hyperplane in the linear vector space. Any questions so far? One of the things that I want you to appreciate, understand, and then appreciate is that how little structure you need to be able to define some of these concepts in an abstract setting. Okay, I know it's somewhat difficult. So the thing that I always tell my graduate students is many a times you study these things, you don't understand it right there and then, you understand it 2 years later. So I'm not teaching you because I want you to understand it today. I'm teaching you because 2 years later you will have a complete understanding of the subject. So you'll have to wait for 2 more years to understand the implications of what we are talking about. But the reason why there is beauty in this is because you need extremely, so, I know for linear algebra, you had to study so much of stuff in order to understand the concept of a hyperplane. But now, by stripping all the details of whatever you have studied in your math classes, all the way from high school and middle school and elementary school, all the way till undergraduate, we are stripping all of that away. And we talked about linear vector space, which had addition and multiplication. We talked about field, which has an addition and multiplication. And just using those two concepts and the set of 7 or 8 axioms that we talked about, I'm able to define a hyperplane, hyperplane in a high dimensional space. That's the beauty in this, in the stuff that we are talking about. Whether you recognize it or not, it is beautiful. Okay. So one fact that is not too difficult to prove, but we won't prove that in the class. So span of W is the smallest subspace containing W. So if I tell you that a subspace, I have a subspace that contains span of W, you know that span of W will be part of that particular subspace. So in other words, like going back to our example, if the subspace I talk about is polynomials up to degree 10, and you know that it contains W, it contains V0, V1, V2, V3, and so on, then it must contain the span of W. Span of W is polynomials of degree 4, and that's definitely contained in the set of polynomials up to degree 10. So it's just saying that in the mathematical language. Any questions so far? Okay. So in the previous lecture, we talked about the concept of linear independence. So we talked about a finite set of vectors. We took a finite set of vectors. We took the linear combination. If the linear combination is 0 and that implies all the coefficients are 0, then it means that the set of vectors are linearly independent. So this is something we talked about in the previous class. Let's talk about linear independence in an infinite set. So now my W is going to be an infinite set. An infinite set W is said to be linearly independent if and only if every finite set of W is linearly independent. Let's construct an infinite set. So W equals to V0, V1, and so on. Okay, so I've constructed an infinite set. What does this infinite set contain? All exponents of variable s. Now the question is this a linearly independent set? Okay. Can I define V2 by a linear combination of V0 and V1? Can I compute S square for all S? Remember, my S lies in this closed interval A to B. A is not equal to B, so this is a finite interval, some interval over the real line. Can I take a linear combination of 1 and S to construct S square, which is equal for all S in A and B? And the answer is no. S square looks like this, 1 looks like this, and V1, so this is my V0, this is my V2, and my V1 is probably going to look like this. This is my V1. So if I add V0 and V1, no matter what combination I can take, I cannot get this curved function. And therefore, I mean, not therefore, but you can argue this for almost everything, not almost, but for every vector in this, you cannot take any vector as a linear combination of other vectors. It's not possible. So this set W, it's an infinite set, but it's actually linearly independent, because no matter you pick any finite set from this, if you take the sum, linear combination of those vectors, those finite sum, if this thing is 0, then each of those alpha is necessarily have to be 0. Okay, so this is a set of linearly independent. So I'm going to write linearly independent. So I'm shortening this word, vectors. Vectors in what? In C, A, B, R. Can someone tell me why we care about linear independence? What's the beautiful thing about linear independence? You know, any of you have taken any courses in fluid mechanics? I presume no one, right? So the good thing about linear independence is that, so if you're not able to approximate something very well using the existing set of functions, it means that you need some other function in order to span that particular function set. So for instance, you are trying to approximate a continuous function. Well, I'm going on a digression here, but if you are trying to approximate a continuous function, you have only two functions, V0 and V1, and you're not able to approximate the continuous function very well. It means that you need to add some other functions that are linearly independent with respect to the original two functions that you started with in order to better approximate the function. So I give you exponential as a function, that's a continuous function. Initially, you started with just constant function and linear functions of s. In order to approximate the exponential using some sort of data-driven way, you're not able to do it very well. Then you need to add another linearly independent function V2 in order to approximate it better. If that approximation is not good, then you add V3 in order to approximate it better, and so on and so forth. So just having a way to generate a linearly independent set of vectors is actually very important when you talk about approximation. I know this class, we don't talk about approximations in this class, but that's one very big application of this statement. And the entire theory of neural network actually is based on some of these ideas. Okay. One more important point I want to make is that whether a set of vectors is linearly independent or not depends not just on the functions themselves, but also on the field f that we have picked for those functions. And I'll give you a very simple example. Any questions on this before I jump onto that example? Okay. So I have my W as 1 over S plus 3, 1S, and S plus 2, S plus 2, S. So I have two functions in my two fractional polynomials in my set W. So this is a subset of fractional polynomials. We talked about this set in the previous lecture. If my field f is R, then these are linearly independent. If my field f is, I should say, vector of fractional polynomials, if my f is fractional polynomial, then W is linearly dependent. So the field that you pick is very important in order to define the linear independence / dependence. By making a small change to the field, you will change the nature of the dependent structure in the space W that you might have picked. Okay. Any questions so far? I'll pause here for a bit and I'll let you digest all this stuff and let me know if you have any questions. Okay, now no questions, then I have to talk about basis. So I have a linear vector space V. I want to find the basis for V. So what is the basis? So W, a subset of V, is a basis for V if and only if W is linearly independent and span W equals to V. Okay. Now, in the context of linear algebra, you must have studied that if V equals to Rn and EI is defined by 0, 0, 1, 0, 0. So this is the ith position. So I have 1 in the ith position and 0 everywhere else. Then the set W E1 to En is the standard basis. Generally speaking, this notion of standard basis is somewhat complicated in the sense that it depends on what you feel comfortable with. I mean, I could come up with some other standard basis for Rn. I mean, some basis for Rn, but if everybody agrees that that particular basis looks good, then we just call it a standard basis. It doesn't have to do with it has to do with what everyone believes to be the usual basis for a specific space. But we won't go too deep into standard basis, but know that for Rn, this is typically set to be the standard basis. So 1 0 0 0 0 0 1 0 0 0 0 0 1 0 0 and so on and so forth. Now we have extended that notion of basis which spans the entire Rn. So that was the notion. Now we have extended this to the infinite, I mean to general setting, just on the basis of some elementary operations that we talked about in the previous lecture. Okay. There is some complexity. I know many of you may not have taken courses in real analysis or functional analysis in the math department, but many a times, especially in infinite dimensional spaces, which I'll get to the definition in a bit, generally speaking, the closure of the span, so span of W may be not a closed set, so you have to close this set and then sometimes that becomes equal to V. So the polynomials of degree n, or rather polynomials, the set W that we talked about, I think it was here, the infinite set W that we talked about, the span of W is not equal to the continuous functions, but the closure of the span is equal to the continuous functions. And the reason for that is, remember that span contains finite linear combinations, right? Not infinite linear combination, but exponential is an infinite linear combination. So sometimes you have to close the set in order to get equal to V in infinite dimensional setting. So what's the dimension of this linear vector space? So if my linear vector space is Rn, recall that this W equals to E1 to En. So it has n elements. So the number of elements in the basis for V is said to be the dimension of V. So dimension of V denoted by dim V is equal to the cardinality of W. So if W is finite, then we say that V is finite dimensional. W is infinite, we say that V is infinite dimensional. So the continuous and bounded functions, so continuous functions over closed interval is an infinite dimensional space. question?
I had a quick question.
Yes, please.
So if W is finite, right, and we know that W is a subspace of V.
No, that W is different from this W. Now we are talking about basis of V. This is old stuff. This is what we did in the previous lecture. Now W has become the basis of V for V, where W is linearly independent and span of W equals to V. Any question so far? How many of you have taken signals and systems? Have you studied the concept of periodic functions in discrete time, right? Discrete time periodic functions. Remember when we did the Fourier transform in those classes, we had only like capital T number of Fourier transforms for discrete periodic functions. That's a finite dimensional vector space. So space of periodic functions, not specially, but in discrete time, if you're taking the space of periodic functions, that's your V. It's finite dimensional because there are finite basis functions, and you can span the entire function using those basis function using n coefficients, and those n coefficients were called Fourier transform, or what were they called? Was it Fourier transform or Fourier coefficient? Whatever, it's called Fourier coefficient. So that was a finite dimensional. But if you had this signal, periodic signal as a function of time, then you had to come up with Fourier transform, because V was infinite dimensional, because you needed infinite number of sinusoidals to be able to generate that specific signal that you had, right? So this is generalizing what you studied in signals and systems. Okay, Fourier transform, Fourier series, Fourier coefficients, so all of that stuff is generalized by this particular statement. So in some cases, you were dealing with a finite dimensional vector space, which is space of periodic functions, discrete time periodic functions with period t, and then sometimes you were working with infinite dimensional periodic functions, where the standard basis was the number of functions in standard basis were infinite. Okay, so sine omega t was the standard basis there, or e raised to j omega t. Okay. The other important example, so finite dimensional, of course, Rn, Cn periodic functions in discrete time. So that's finite dimensional, and infinite dimensional is C A B to Rn. These are infinite dimensional spaces. Much of my research actually is for infinite dimensional spaces. So I work a lot with infinite dimensional spaces in my research. Okay, let's talk about linear transformation. Any questions so far on the dimension of V? When something is during the course, sometimes it will be convenient to live in a finite dimensional space. Sometimes it will be convenient to live in an infinite dimensional space. So we'll keep switching between finite dimensional and infinite dimensional spaces during the rest of the lectures. Linear transformation. So I know you've all studied matrices, and now you are all experts on matrices. Now we are generalizing matrices to potentially infinite dimensional spaces. So I have two vector spaces, two V and W are LVS, linear vector spaces, T maps V to W is linear if and only if Tx plus y, Tx plus Ty, T alpha x equals to alpha Tx for all x, y in V, for all alpha in F. So in this case, V and W have the same F. The field is the same. They're not defined with different fields. So the same field, they both are linear vector spaces. They could be any dimensional linear vector spaces, but T is a linear transformation. What was a linear transformation in your ECE 3050 signals and systems? Anyone remembers? Fourier transform was a linear transformation. Okay, so we had the e raised to j omega t, e raised to 2j omega t, 3j omega t, and so on. And W would be the space of signals, or vice versa. And you do either the Fourier coefficient or inverse Fourier, either you do the Fourier transform or inverse Fourier transform. Both of them were linear operators. Now we are generalizing it. Okay, so in matrices, you talked about T being matrices and X being vectors, X and Y being vectors. In signals and systems, you talked about e raised to j omega t as your primitives, and now we are expanding this definition to linear vector spaces. Okay, so generalizing all the stuff you did during your undergrad into a single mathematical framework. Okay. So simple example, X is in Rn. Well, let me start with V. V is Rn, W is Rm, T of X is defined by Ax. A is a matrix in Rm cross n. So if I give you a linear transformation, so here is the fun quiz or fun exercise for you to think about right now. I give you a Python API or a MATLAB function where you can input the function x, and I'll give you T of x, and I'll tell you that it's a linear transformation. Okay, that's all. But I'll hide that particular function from you. Okay, how will you reconstruct this matrix A? Okay, what's the quiz here? So I have an API where you can give as input x, and the output of the API is T of x, and I ask you to reconstruct this matrix A. How will you do that? You know that it's a linear transformation. I've told you that it's a linear transformation, and I want you to reconstruct this matrix A. Any idea? Yeah, any wild guess? Yeah.
You feed it the basis of x.
Yeah, you can feed the basis of x. So what kind of basis would you like to pick? Just the standard one?
Yes.
Okay, so let's say you fed 10000, and the output of T of E1, so this is my E1, T of E1 was A11, A21, A31, AM1. So you will do the same thing again and again. So now you have all these vectors. How do you get this matrix A? So this is a vector in Rm. So you get like n vectors in Rm. I want you to reconstruct this matrix A. What will you do? Yeah.
So you just take the first row of A would be the transpose of T of E1.
Remember, A is a matrix of size m cross n, so it has n elements in a row and it has m elements in a column. And what you are getting here is an m element because this is an Rn. This is an Rn, but T maps Rn to Rm. So what you're getting is an m-dimensional vector. So how would you reconstruct A? You are actually quite close. Yeah.
Take the transpose of this.
So I have n such vectors. Which vector do you want to take the transpose of? How do you reconstruct this matrix A? Yeah.
That is the first column thing.
That's the first column of A. So you give it an input E1, you get the first column of A. You give it an input E2, you get the second column of A. You stack all these columns together, you get the matrix A. So the important or the cool thing here is, if you have a linear transformation, the way to know how that linear transformation is going to behave, you just keep feeding it the standard basis, whatever your favorite basis is. It doesn't have to be standard basis, whatever your favorite basis is, and it will give you the performance of that linear transformation. You can reconstruct that entire linear transformation after a certain number of API calls in this case. So in this case, you need to have n API calls because V is an n-dimensional space, right? If V was infinite dimensional space, how many API calls do you need? Infinite number of API calls, okay? So in n-dimensional, life is easy. In infinite dimensions, life becomes hard, which is why I'm making your life hard in this class. Okay. So the fun thing is, if there is a linear transformation, you know it's a linear transformation, you feed it the basis vector, you can reconstruct that linear transformation. There are a few cool things about linear transformation. So let me make sure that I'm using the right terminology. I think it's called null space of A. Yeah, null space. Okay. So I define null space of T. Well, null space of T denoted by null of T is the set of vectors such that TV equals to 0W. Range space of T Okay, so let's think about it. What's the dimension of V here? 3. What is the dimension of W? 2. This is a 2-dimensional plane. This is a 3-dimensional object. Euclidean space. T is my linear mapping. What's the null space of T? It's the vectors V that T nullifies. Okay, so if T operates on this vector V, you get a 0 vector in W. So this is your 0 vector in W. This is 0 of W. And so I have this, let's say there is a hyperplane passing through origin. This is the null space of T. That's the null space of T. So it's passing through origin. No matter which vector you pick here, you apply T here, it gets mapped to 0 of W. Okay, the 0 vector in the W space, W LVS. What's the range space of T? So range of T is the set of W that you get if you apply vector V. So you have a vector V here, you apply T onto that particular vector and you get some space or subspace which is the range of T. So this particular subspace is the range of T. It passes through origin. Okay, so the cool thing is, because T of 0 will always be 0, so null space will always have the 0 vector of V, and the range space will always have the 0 vector of W. So both of these are non-empty sets. Okay, at least 0 lies in that particular set. Is there something else that you notice? You know what I notice here? The dimension of V is 3. The null space of V is 2-dimensional. The range space of V is 1-dimensional. So the dimension of the null space plus the dimension of the range space gives me the dimension of the vector space, LVSV. So dimension of V, this is known as the fundamental theorem of linear equations. Dimension of V equals to dimension of null space of T plus dimension of range space of T. Any questions so far on this? We are not going to prove this result. You might have already proven it in linear algebra class, but this is again true in general dimensions as well. Okay, what else? I want to talk about one-to-one functions. So T is one-to-one, also called injective, if and only if T of V1 equals to T of V2 implies if and only if V1 equals to V2. and onto. T is onto surjective if and only if for every W in W there exists a V in V such that TV equals to W. Okay, so what is the cool thing about injective map? If you see an output of a function t, you can trace back what the v was from which that particular vector was generated, right? So because two vectors will always generate two different outputs. Okay, so two distinct v's will generate two distinct outputs. So if you know the output, you can figure out what the input to the function was. That's the benefit of being injective. What's the benefit of being surjective? Every vector in the space W in LVSW can be generated by a vector V in the space capital V. Okay. So if you have a robot, you want that robot to move to a specific point in the space. You want that mapping of the dynamics of the robot to be surjective, because then you know that every point in the configuration space there exists an input that can generate that particular configuration. So therefore the robot can go anywhere. The injective means that if you see the robot at a specific place, then you know exactly what input generated that specific behavior of that robot. Okay, so T is invertible if it is both 1, 1 and onto. So T is invertible if and only if T is 1, 2, 1 and onto. This is known as bijective. So if T is bijective, then it is invertible. If T is invertible, then T is bijective. So invertible matrices that you must have studied in linear algebra, that's a invertible transformation. Fourier series, Fourier transform, all of that work because those are invertible transformations. Invertible linear transformation. If taking Fourier series was not invertible, we wouldn't be teaching you 3050, okay? Because 3050 wouldn't make any sense. Signals and systems and feedback control systems would not make any sense if T was not invertible. Okay. Any questions so far? Let's look at, we did see one example of T, so let me show you another example of T, I think, because we are talking so much about Fourier series. So if your V is continuous and bounded function, I can define my TV as integral from A to B of KST Vs ds. Oh, TV is a function of small t. So this is a linear transformation. And in the case of Fourier transform, this k function actually is the e raised to j omega t function, or e raised to minus s t function. Okay. So that's a valid linear transformation. And it's actually an invertible linear transformation. That's why you can take Fourier transform and then you can take inverse Fourier transform, or you can take Laplace transform and then you can take inverse Laplace transform. So these are all invertible operations. That's why we are teaching it in undergraduate class. Any questions on this? Okay. Similarity transform. So sometimes we want to go from one space to another, one set of basis functions to another basis function. So we study this under the umbrella of similarity transform. So my V is equals to W, and my T is a linear operator or linear transformation from V to V. I have two basis functions, V1 to Vn. Let's assume these are finite dimensional. So V is finite dimensional. V1 to Vn is and V1 bar to Vn bar are basis. Perfect. So these are bases. So I can come up with a linear transformation matrix. So V1 equals to P V1 bar, V2 equals to P V2 bar, Vn equals to P Vn bar. So I came up with a linear transformation P that maps the basis vectors to each other. And then I define a transformation A bar equals to P inverse AP. This is a mapping from V to V. And this is known as similarity transformation. How many of you have seen similarity transformation earlier? Everyone? Okay, so what are we doing in similarity transformation? So I have I have a finite dimensional linear vector space. I have a linear operation, linear transformation. That linear transformation is essentially TV equals to AV. So it's just a matrix multiplication. I have two separate bases for it. I can pick the standard basis, or I can pick maybe some other basis for Rn. Okay. Now, what I can do is I can define a linear transformation that transforms those bases. So it goes from one basis vector to another basis vector. It turns out that you can also do transformation of this linear operator T, so that in the new basis vector, you get the same linear transformation. So the transformation itself hasn't changed. So whatever vector V you started with, you will get the same vector, same output. It's just that you are now looking at this particular problem in a different space, or in a space with the different basis vectors, and so that's why it's called similarity transformation. So the good thing about similarity transformation is that it doesn't change the eigenvalues and eigenvectors, which is what I'm going to talk about next. Okay, so the goal of similarity transformation is to get a transformation under the updated basis. And those of you who might have taken robotics class 5463, you would know that many a times it's important in robotics to keep changing the perspective from which you are actually doing the computation. So it's a very similar idea is embedded here as well. I'll go fast on eigenvalues and eigenvectors because I know you guys are very familiar with it. So I have a matrix A, which is in Rn cross n. Then lambda is an eigenvalue and V is the corresponding eigenvector if and only if AB equals to lambda V. And the fact is, similarity transform does not change eigenvalues. Okay. So characteristic polynomial is P as a function of lambda given by determinant of lambda I minus a. And the roots of P lambda eigenvalues of A. Generally speaking, for general matrices, the roots of the polynomial lies in complex plane. It need not always lie in a real, not a complex plane, but it's yeah, the roots will be in complex plane, not in real line. So so something to keep in mind, that eigenvalues of matrices could be complex numbers. Okay. You know, I'm thinking about whether I should start a new topic, norm. How many of you have heard of this term norm before? Norm? Okay, so maybe I can start then. It's not really a new topic for you. Norm. So I have V2 0 infinity. So norm is a function that takes as input a vector from the linear vector space and outputs a number between 0 and infinity. It's a closed interval on the 0 side but open interval on the infinity side. Is a norm if and only if it satisfies three criteria. The first is positive definite. Norm of V is greater than equal to 0 and norm of V is equal to 0 if and only if V equals to 0. The second one is scaling in the norm. Okay, it doesn't say what the name is. I think it has something to do with scaling, but basically norm of alpha V equals to alpha times norm of V. I'm pretty sure alpha denotes the this is the absolute value of alpha, and the third one is V1 plus V2 is less than equal to norm of V1 plus norm of V2. This is known as triangle inequality. Okay, one important note here that alpha could be real numbers, in which case this is the absolute value. It could be complex numbers, in which case it would be the modulus of the complex number. Okay, typically speaking, it's easy to construct a positive definite function. It's sometimes easy to construct functions that satisfy this. It's extremely difficult to construct functions that satisfy this. So it's the triangle inequality that truly changes the is really the binding factor here in the definition of the norm. So typical norms, I know that on the real line and Euclidean spaces, you know about this L1 norm. L1 norm, so denoted by this summation of absolute value of xi, I equals 1 to n, x is in Rn. L2 norm, and then L infinity norm. So on the Euclidean spaces, I think the norms are something that you have seen many times in the past. So LP norm, L1 norm, L2 norm, and so on. You could construct even more interesting norms. on this space. For matrices, a very good norm is Frobenius norm. So trace is TR is the trace operation. So you take A transpose A, that's Frobenius norm, AF. There are many other matrices norm also, but Frobenius is important. And then on the CAB are, maybe I'll do Rn. There is L1 norm. So A to B, FS, DS, L2 norm. I know generally you can pick any norm here. You can pick one norm, two norm, P norm, because this Fs is a vector in Rn. But generally speaking, I think people tend to keep two norms because it's easier, everybody understands two norms well. But when you are dealing with abstract linear vector spaces, you can pick any norm of your choice here on this side. Okay, any of those norms are fine because those norms are norms over Rn. L infinity norm. So L infinity norm is typically designed for CABR. So for CABR, you have L infinity norm, which is so these are all the important norms we will need over the rest of the course. Any questions on these norms? Maybe I have a question. So if I say F2 is 0, the norm L2 norm of F is 0, would you be able to conclude that F is equal to 0? Is it easy to conclude? So my question is, my norm F2 equals to 0. What does this imply? Remember that norm is equal to 0 must imply that the function itself is equal to 0. Okay, so F2 is 0. What? Oh, I'm so sorry. I'm supposed to put a square root here. I didn't put a square root. So please put a square root here. So F2 is 0. It means that square root, well, I don't want to deal with the square root right now. So I'll just make the square equals to 0. So then I have A to B Fs ds equals to 0. Okay, does that imply f is equal to 0? I know if f is equal to 0, then I can prove this expression. It's very easy. But I'm asking the converse. I'm saying that this is equal to 0. I want to show that f is equal to 0. Can someone give me an argument for that? Yes, please.
Well, if f was not 0 at any point in the whole interval, then it would not be 0. So I guess I don't know if it's some kind of contrapositive.
It's a contrapositive statement, yeah. Yeah, so contrapositive statement works. I don't like proof by contrapositive statement. So his argument is, suppose this is non-zero, but this statement holds true. If this is non-zero, then this number inside is positive because of this requirement. So this number is positive. I'm integrating something positive over an interval. It must lead to a positive value because you're adding things up, adding positive numbers up. It has to lead to a positive value. So that's a contrapositive statement. A and not B leads to a contradiction. Therefore, A must imply B, something along those lines. But we can actually make the argument, typically speaking, you can make contrapositive statement generally a usual statement by saying that if this is equal to 0 and this is always non-negative, I guess proof by contrapositive is much easier. Let me think if I can prove it without the contrapositive statement. I generally don't like contrapositive statements, so it's a fun exercise for me to think about how to prove this without using the contrapositive statement. But anyways, any other questions on this stuff? Okay, so no matter what norm you pick, no matter which of these norms you are picking, you can easily show if Frobenius norm of a matrix is 0, then the matrix must be 0. If L1 norm of a function is 0, then the function must be 0. If infinity norm of a function is 0, then the function must be 0, and so on. So all of this can be proven fairly easily, and therefore they all satisfy. And the fact that they satisfy triangle inequality is also somewhat non-trivial. Maybe we'll talk about it in the next class, but those are the things that we'll start from this statement of the norm, and then we'll build inner product and so on and so forth. Yeah.
If we increase B and A, maybe if we can show that this one is monotonically increased, can we?
No, the point is you can't use the monotonic argument because this A and B are fixed when you're defining the state, when you're defining the linear vector space. Yeah. But there are places where we need to make that argument. When you have minus infinity to plus infinity, then you have to make those arguments. All right. Thank you so much, and I'll see you on Tuesday next week. Have a great long weekend.